What's up, everybody? Welcome back. Today, we are working on trying to abuse color calibration in in KDE's Wayland compositor as a way to make it so that I can see things in video games without getting frustrated. So, I've been playing a lot of Arc Raiders. It's really freaking dark. Like, really, really dark. And I can kind of make it playable if I go into my monitor settings and like change the gamma curve that the monitor is using to basically like kind of boost dark areas. You might argue that's cheating, but like I don't know, man. It's like a button on the monitor. I don't know. Like I think it's fine. But it's frustrating because that makes all of the other stuff that I do on my computer look fucking weird, right? And so what I would prefer is if I could do that in software. Basically say, when I play this game, I want my monitor to output a different looking thing. And there are many ways you could go about this. The Linux graphics stack is a little complicated. But basically we have like game, right? We have kind of like the protons or wines direct 3D shader to Vulkan shader pipeline. You could apply something here. This stuff kind of goes into some like window provided by Kwin, right? So Kwin kind of decides to render a window that this guy gives him. And then Kwin kind of talks to the GPU directly because we are in Wayland land and these guys kind of speak Wayland to each other. Hand wavy. We kind of want like a fast way to do this on GPU. So doing at like the Vulkan layer, I believe would result in like an extra shader pass that we don't really need for such a simple transformation. In fact, when we were looking at Steam's kind of mini Wayland compositor that they use on the Steam Deck, they're kind of saying like, hey, we have shader support, but if you're trying to do just like color correction type shit, don't use that, use lookup tables. And so Kwin owns access to the GPU. So we need to say, hey, Kwin, can you apply these color curves for us in some way to make everything look brighter? And Kwin will say, okay, but the thing is there's no like API for that. The only API we have is ICC profile color correction, right? So this is kind of used for, I staple some scanner on my screen. I want to have like work with photos that look correct. So I use this calibrator to say, hey, this is what if I like show it all the different colors that my monitor can output, it can kind of say, oh, this one needs to be a little darker, this one needs to be a little lighter, and he can like give us a lookup table and we feed that to Kwin. Kwin fixes it by applying it to the GPU's output. So we want to generate these profiles that basically keep the monitor almost how it is and adjust it just a little bit. So our last stream, we managed to successfully parse a profile, and we kind of found out what's in here. So there is kind of like a big profile header. These profiles kind of are designed to work in this thing called profile connection space. So the idea is that like I take a photo on my camera, the camera will have a profile maybe that says, hey, I output like this, and I have like a calibration for this camera that kind of adjusts the outputs like this. And that I'll put this in this common space, and then I will feed this output to my display, and this display will have the same calibration stuff, and he will know how to like convert between these two areas to display this particular image in like a color corrected way, right? So in this thing, what we have is a matrix here. Okay, we have like a definition for what our calibration device considered white. So in this calibration space, there are many maybe definitions of what white is. There's this thing called like D illuminant D or something. We were reading about this yesterday in Happy Hour. But basically, like the color consortium people or whatever, the International Commission of Color, whatever, they have some things that basically just say like, hey, when I look at white light at like different things, we have some curve that kind of like approximates the like frequency distribution of that light, and they have like numbers that they have for how do I say this, like specific types of white. I don't really remember. There's like D50, D65. I don't remember what they all mean. But this white point header that we have in here basically says this is the white point that we use for calibration. So in the sample files we found that there's like D65 white point is being used, but the profile connection space wants D50. That'll become relevant later. We also set a black point, which we can probably just set to 0, would be my guess. Then they have this like matrix. And what is this matrix? It's like it's however you want to be working in your profile. I need to be able to convert that to the common space. So this RGB stuff basically defines the transformation from your space to common space, including doing things like adjusting the white point. So this we found yesterday in Happy Hour stream is a matrix that we can get to look a lot like the matrices that we have in our sample files if we do, we use sRGB's color matrix to convert to like the correct space, plus a scale matrix to adjust the white point. And you might say, what the fuck is sRGB? And I'd be like, that's a reasonable question. So I will get there in a second. The rest of this stuff is basically curves for how your monitor should output different values for RGB in an image. Hand wavy. So you would expect that on a normal monitor you might have a curve that looks like this, right? For each input, just make the output the same. No, wrong. Incorrect as far as what we've seen so far. What we see is actually something more that looks like this. And the answer to why it looks like this is because there's this thing called sRGB, which basically says we encode all of our images like this. Why, you might ask? Well, my understanding from what I've read so far, which could very well be wrong because it's very confusing and I'm lost, but my understanding is that back in the day, you had monitors that were CRTs, right? Cathode ray tubes. And in here, you've got a gun in the back of this box, and he's shooting radiation at this screen that catches it, right? So when you see like movies like The Matrix and they all have like green text on here, it's just because like the screen that they're shooting the gun at is green. They eventually figured out how to do colors on here. But like, so what's happening is the gun is kind of like back here, and he's kind of like ripping back and forth on this screen, trying to like rapidly paint everything. And the numbers in our, the like pixel brightnesses in our RGB in our image file is basically like going directly to the gun. And so the gun, has a response curve that looks like this, right? So basically for every change in power that you try to give it, the like effective brightness that like a human sees, you know, like what my eyeball sees here, is like not linearly related to this thing. And it turns out that this is like approximately equal to like x to the power of 2.2. So when we talk about like gamma adjustment, we're like changing this exponent to kind of like make this curve look like this. And that's why. And you might say like, okay, we don't use CRTs anymore. Why don't we just fix this? Well, one, we started encoding all of our images backwards to like fix this. But also it turns out that we can see changes in darkness a lot better than changes in bright. So it's actually, by encoding our images like this, we get like a lot more resolution in the darks than in the lights, if that makes sense. Like, because the x-axis here is like brightness, right? So like here we're kind of trading based off linear, like all of the whites are getting squished here and all of the darks are getting kind of like expanded here, which gives us kind of just more resolution in the dark area, if that makes sense. So all of this to say, these curves that we put in here, if we want them to do nothing to the monitor, should kind of approximately encode the sRGB gamma curve, because all of our images are encoding under the sRGB specification, which is this like curve shit that I was just talking about, right? Like this gamma shit. So that kind of covers all of this stuff we have to put in here. We put in, so if we want to create something where my display will have no changes, we create some tone curves that match a gamma curve and we shove them in this file. We create a matrix that converts from our RGB space to the like color consortium standard space. We set our white points, And I believe that the other stuff is not required, based off of the spec we saw. What we can parse right now is most of it. We can parse the white point, we can parse the RGB matrix, and we can parse a curve. We are capable of doing all that right now. So the goal for today is to kind of do the opposite of that and output a file that we can load that works the way we expect. Now, an extra piece of information here is that you guys, when I apply these ICC profiles to my monitor, can't see them. Because OBS is not recording the output of the monitor, he's recording like the output of the compositor, which is not applying this, right? Or more like he's recording what the compositor chooses that he is allowed to record, which doesn't include this stuff. And so we have been using, we can use like MPV, a video player, to test these profiles. However, all evidence that we have so far kind of like indicates that MPV applies a curve and then the monitor applies the curve. So we might start doing something like trying to make a completely linear curve or something like that. But we'll kind of see where we end up. So, to do, we kind of have what we did our intro, which was very long, but there's a lot of context because we read a lot yesterday. Then we have, I guess it's like, generate any profile. So, probably our first profile is maybe like linear, no change, and then maybe, generate like no change profile, I guess. We'll do this. Generate no change MPV profile. Then we will try to maybe generate like tint red profile or something that we can see an effect on that's like really simple. Then maybe like confirm, like add sRGB for monitor at end so that we can kind of like, I can test that, which you guys won't be able to see. And then I'll generate arbitrary gamma adjustment. I think that's kind of like a good set of plans for the day. If we can get there, I'll be very happy. So I guess let's get moving. So I guess the first thing that we want to do is we want to take one of these samples and we want to maybe try to like reproduce the header that we parsed, right? So we are parsing something of this guy. And maybe the thing to do is to write like a serialization function that takes these options that we parsed, writes them back down, and compares the outputs and says that they should be the same. I think that's the first step. So in here, we should have some sort of like, I don't know, write header, which is going to take in whatever our header looks like, right? So we have a header right now. Right header. And this guy will also take a writer where he's going to put this stuff. And I guess here we just need to do the inverse of parsing, right? So we have a parse here. And I guess we just go the opposite. So it's like W write int of header profile size in big endian mode. Then we write the preferred color management mode. So here, this is interesting. We have like parse on preferred CMM here. So what is this thing? This thing is basically just a packed string. So we have these kind of in some fancy way, but it doesn't have to be like that, but it's okay. We'll just say, what, like we need self here, and we need to say write all of self inner. I think that's fine. So now for this guy, we can go try W, I guess it's like header preferred CMM write into writer. Okay, easy. And then we have the same thing for profile version, device class, and color space. All of this stuff is the same. In here, did I write it wrong? Yeah, I sure did. Thank you. I sure did. PCS as well, which I mean, a lot of these things we don't even know what they are right now, and it doesn't really matter, right? We're kind of just trying to feel out something here. Date is a date time number, which is interesting. This guy we probably have to parse correctly because we're gonna be generating these at some point. Uh, actually parse and write. But for now, we will just copy whatever they have in theirs, and we'll call it a day like that. And so here we will say header. I guess it's like a w write struct of date time number with big endian, just the inverse. Then we have a couple of these guys. Maybe it makes sense to copy paste this and kind of modify them instead, right? So anything that says parse, we're gonna do try header dot and then delete to the parse and write right like this. Okay, so another parse here, parse, okay. These guys are all take int style, so this is all gonna be try w write int header dot this and with big endian. Boom, boom, boom. And then these take arrays are going to be written. And so I guess it's likely that this profile ID, we haven't parsed these yet. And reserved, I think, is just 0. So I guess we'll figure it out. So profile ID here is, I think this is just for display. Not sure. So this is w write all. And then I think the reserved is a little w splat zeros. Okay, cool. Okay, that looks close. Rendering intent does not have a write function on it yet. Or creator does. NCIE XYZ is an XYZ number, so this does not yet. Which looks like we have, it's literally just huck 3 numbers at it. So we need to write a write function for this. Self is a XYZ number. Writer is a std.io writer. Okay. And he's like, try w write. Nope. Self x write w. And we have YZ. And this just has to be the opposite of whatever they have in parse for this thing. By they, I mean us. So write means we have to pack this stuff into an I32 or a U32. So the sign is the top bit. So we have like var val is a U32 equals sign. Which we put here. Then we shift left by 16, I guess. And we say val or equals self integer. And then we shift left by 15. And we say val or equals fractional. And I believe that makes the same thing. And then we can do try w write int w with big encoding. I think that's right. I don't know. We'll see. We will see pretty quickly. Are we... Where is it? Right header? Are we missing anything else? Rendering intent. This is a rendering intent. So write takes in self as a rendering intent. This looks like an enum of some sort. We are writing instead of reading. Beautiful. And it looks like we just write the int. So this is just like w write int as a u32, and we do int from enum of self, and we encode it big. Easy. Easy peasy, man. Okay. And so now all we want to do is what? I'm not gonna click this link, but I'm also not gonna ban you. But a first time chat to a YouTube link is a no-no. I don't know if that yeah. I would click it and then ban you once I found out what it was. But lucky for you, I don't want to click it. So you win. Okay. So now we want to do like a test, like profile header round trip or something, right? And I guess we want to read header from somewhere. From like sample buff, right? We probably have like sample is this. So can we hex dump this guy? And can we take how long is the header? How long is the header? I guess it actually probably makes sense to just maybe embed this as a sample, right? sRGB 1.0 ICC to sample to res. We can kind of say here that in our test we have embed file of res this guy. And in here, then we can do sample reader is stood IO reader fixed. On sample, we read this from the sample reader. Uh-huh. And then we try to write this thing out, right? So we write header, H into some outbuff or outwriter. So we have some sort of output buffer, and we create a writer around this thing, like this, and then we assert that these are the same. So probably sample reader, how much of this have we read? Should be equal to what we wrote. Something like this. He's gonna be mad because sample reader was already a pointer. Write header expected 3 arguments, found 2. Am I stupid? Oh, it at 321. Okay. So this write int. Oh, do we need to write the type? Interesting. Profile. Whoa. Oh, this guy has to be failable. Would it be possible to make the text a little bit larger? Yeah, sorry. Did I just forget? I usually do that. Thank you. Good eye. Good eye. Yeah, there we go. I agree. I agree. Profile version needs a write. So we just have the inverse of parse. And what does this look like? We have take byte. So major. So write byte major. Then they take another byte for minor. This is, oh, we pack the minor and patch together. So minor patch is a U8 is equal to self minor. I guess we just do this. Self minor. Yeah, the types are going to be easier if we do this like this. Minor patch shift left by 4, and then minor patch 4 equals like this. And then we write that. So we go Write byte of minor patch. And then they discarded 2. So we should write 2 empty bytes. Splat byte all 0 2 times. I think that's right. I think that is right. Not a struct. Right, because at 338 we did give him a type instead of just the thing that we're trying to write in there. Write int here. All of these guys are probably U32s. We should check. U32, 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 U30, C64. Expected 3 arguments found 2. This is U32, surely. Surely. And then he thinks he's returning, which he's not, because we're writing. We are not reading anymore. Okay. Close. So all of this stuff was the same. Beep boop beep boop beep boop beep boop. But we shifted. This looks like a shift left bug, right? So we have 0100 versus 80. So probably where is this is the question. Right. Header. I mean, it's pretty easy to bisect, I guess. It's going to be one of these more fancy guys. It's not going to be this, like... It's near the end, right? Because this is all the reserved stuff. So it's like 1, 2, 3 back from the last one, right? So it's going to be NCIEXYZ or creator or something. Or rendering intent. So can we just do this, actually? And then it'll become pretty obvious. So we can write a little more. And now this guy is the guy bugged. So here we tried to write XYZ. Whoa. Okay, so we tried parse X, parse Y, parse Z. And so it looks like in the signed thing, this is the bug. So what is it? We expected 0100 and found 0800, which makes me think that the sign wasn't pushed far enough, or maybe this guy wasn't pushed enough. No, because this is too much shifting. Self sign. What am I missing here? Shouldn't industry shift by 15? I think that's where it started. I'm just gonna do something stupid for a second. Okay, so this does do it. Oh! Wait, is it like that? Yeah, there we go. So we put the sign in, we shift left by 15, then we pack in the 15 bits of integer, then we shift all of this by 16 for the 16 bits of fractional. That makes more sense. That makes sense. I agree. And we bring this back. All right, our back and forth test is working correctly, so we can write the header out. We have a couple pieces that we can't generate from scratch right now, but we'll figure that out later when we get to that point, which will be soon, probably. So I guess we are going to say we have a new main. And what are we doing it? We are trying to generate a header from scratch, right? So what does our existing header give us, I guess? Oops. Sorry. I guess for now, let's have it so that our args need to take in a like mode. No mode. And here we'll say, if stood mem equal mode to write or read, then we can do whatever the fuck we were doing before, and we can kind of keep this around for convenience. And then if the mode is right, we can start doing something else. Hello? Oh, there we go. Easy. Easy peasy. Okay, so now we can like zig, run, main zig, read our test profile, right? He's mad because this is main, not main 2. Cool. And we could just copy paste this profile and kind of figure it out as we go, right? Okay. Oops. So really this header shouldn't even parse the reserve, to be honest. That shouldn't be in there. So we should just do like R discard limited 28 or something. That's a little bit better, and then this guy shouldn't even have reserved in here. Like this, I guess. Cool. So the test still passed, and now that kind of makes some of this look a little cleaner, so we don't have to stick out reserved. Get that shit out of there. And I guess we have header is like this. And the profile size will have to be like juice later. So we have like profile size is 0 for now, but we'll say fix me like write profile and figure it the fuck out, right? Once we have that information, we can create something reasonable. Preferred CMM. So we had Argle before. Why? Can we look at the ICC profile spec? Right. We need to know what we're trying to do. So we have what chapter was this in? What chapter was this in? What does Argle even mean? Profile header 7.2. C 7.2.3. So if used, shall match a CMM type signature registered in the ICC tag registry. If no CMM is identified, this field should be set to 0. Okay. Can we look for Argle? Am I high? Clause 5. Conformance. Am I stupid? Preferred CMM type bytes 4 to 7. C clause 5. This field may be used to identify preferred color management mode, I guess. Can we just write 0? I don't know. Let's write 0. And this thing, I guess we were going to write maybe null here? And this packed string guy is going to have like const null is, oh, we can't do that. Okay, whatever. We'll just write inner is splat 0. And we'll say spec says we can fill with zeros if we don't care. Smile. Argol is a famous open source color management system. Got it. Got it. Okay. Profile version. I guess we just match it, right? Oh, interesting that we have major 2, minor 2 here, because I think that the other thing that we had as our sample was 420, which maybe we should use as our reference instead here. So can we comment this out for a second? And we can run this with sample, profiles, profiles, sample. What do these guys write? 420. That makes more sense. So we're going to take these guys as our other reference and write that down as well. So this is a sRGB sample. And then we have our other sample. I don't know. Okay, so 420 I think makes more sense for us. I think. Easy. I think device class on monitor is correct for both. That says we are working for a display device, which we are. Which can't be displayed like this, by the way. So fix me, like, I guess this should be like init like this. Probably is what we need on here. And what we'll do is we'll return this, because this is an inline array. And in this, we will go, var ret is this, undefined. We memcopy this in, and then we return ret. Okay, so then we can go like this, init monitor, great. Great, 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 great. Preferred is Apple in that other profile. Yeah, so you have Argol and Apple in 2 of them, and I think I just don't really give a fuck. Both of them have color space RGB. And then I think you need to shove a space after, right? Because that's what they have here. PCS, what does that stand for again? C727. For all profile classes other than device link, this shall either be PCS XYZ or PCS lab. We'll just do XYZ because that's what everyone else did. The profile connection space, as they say. Date, I'm just going to yank from someone, but fix me, actually write a sane date. But for now, we can be cheaters. Filthy little cheaters. Whoopsies, what the fuck did I just do? Filthy, dirty cheaters. Easy peasy. Okay, then we have ASCP, which is what again? Profile signature C729. This profile signature field shall contain the value ACSP. Okay. Which I spelt wrong, by the way. It should be ACSP, but fix me ACSP. I just don't want to fix that right now. Primary platform field. This field may be used to identify the primary. Oh wait, hold on. Yeah, the platform thing. If there's no primary platform identified, set to 0. We set to 0. I don't give a fuck, dude. How did I do this last time? I did like this. I did inner is splat 0. ID care. Flags is interesting. I don't think we ever really parsed these. So what does our flags look like? 0, yeah. Okay. I think that's fine, because we don't have anything that we care about. Device manufacturer field can be set to 0. I don't care. Can we do this? Const. Maybe it should be like packed string in here. Could have like a don't care. Is this is equal to like this. And then we can just kind of huck some don't cares around. Yeah, I like that. I like that. And then I don't have to write I don't care as a profile either. So wait, what were we on? Manufacturer? Model, manufacturer, yeah, let's just shut. I don't give a fuck. Manufacturer, don't care. We have device model, also don't care. Device attributes, 0, probably. Relative or glossy matte, yeah, I don't give a fuck. Yeah, we just don't set any of these bits. Everything is empty. Fine. Rendering intent, is that next here? Yeah. I think both these guys were media relative, which I believe is true. We want to work in the color space of the media, not in like the fancy schmancy XYZ color space. What is going on here? PCS illuminant field. Is that, why did I call that NCIE XYZ? Am I fucking high? Yeah, this is the white point, right? I believe that's what this is. 60, this is 68 to 79. This sounds more like a white point. The PCS illuminant field shall change. Yeah, I'm high. So this should be PCS, was it? Illuminant. I'll fix this one now, because that one's actually like really fucking confusing. And I believe both of these are saying the same guy. And we should be able to initialize this from a floating point number, I think. Because then we can write down what's in spec, right? So they're saying that we should write this. So we should be doing like x equals from F32 0.964, y equals from F32 1.0, and z equals from F32 0.824. And these are the illuminant value of the D50 white point, if I remember correctly from the reading yesterday. And so we need to implement from F32 on this guy. Oh, not this guy, on this guy, sorry. So we have two F32. Probably from F32 is going to be somewhat sane. We probably want to do a test back and forth on here, too. S15, F16, float back and forth. And this is just a little, like, in 0.1234, maybe, like, 5, negative. Maybe we do, like, tests. Like, vowels is going to be, we'll do a positive, which is, and 0.123 or something. This should cover a lot. Didn't you forget 2 at the end of the X coordinate? Probably. I don't know. We're pretty fast and loose right now. Oh, I thought that 2 was part of, I thought that 2 was saying the next thing is a 2, but you're right. There's just a space in these numbers, so I forgot the 9 here as well. Good eye. Back and forth, so we're gonna do some sort of for vowels val. We're gonna be like, I don't know, S fixed 16 from F32 val, and we'll say fixed float is fixed to F32, and then try stood testing, expect a prox equal of val to the floating point within some small margin. Right? Maybe there's a little bit of error there. Okay, and then from F32 here, we need to get the types right. And what are we doing here? So we have something like, we take the fractional bits, so mod self, 1. Is there like remainder? Like, is there like a fractional remainder? Yeah, it's just like this. Fractional is this times 2 to the power of 16 to get it positive. I think, right? Because it's divided by 2 to the 16 here. And then we have integer is div trunk. I guess it's like, it's actually just a cast, right? So this is as a U15 from the absolute value of self. And we should call this val instead of self, I think. Cool. And this is now int from float, which will truncate. And then we get the sign, so stud math is... How do we like extract the sign bit from the float here? I'm sure it's possible in Zig, but I don't know what the API is. Does the idiot know? He probably doesn't. Zig's too new for him, but we can ask. Does Zig have a function to extract sign bit from F2? We'll see. Sometimes he gets it. He's literally just writing it himself. There's no fucking way, right? There's no fucking way. He's a fucking idiot. You're saying it's in math? There's copy sign. Oh, here, just sign bit. Nice. Returns whether x is positive or negative 0. Wait, that's not what I want, right? Maybe that's a bug though. Gotta be, right? Oh, maybe it's just a sign here. Returns -1, 0, 1. Supports integer and float types. I think I just want sign bit. If const sign is if this 1 else 0 or something. Returns whether x is negative or negative 0. I misread this. Whether x is negative or negative 0. So this is going to be negative if it's negative. Chill. I think that's right. So we return this guy now, and we can just go like this, boom. Fractional integer sign, and then we remove the semicolons, replace with commas. Wait, why is he pissed now? Oh. Easy! Zig test. Undeclared identifier profile size. So true, dude. Unused local constant. And able to resolve comp time value. I guess we do this. Expected U16, found F32 when we did times here. So float as F32, float from, can I just do this? Because it's a comp time int, so it should cast without needing some sort of bullshit. Oh, wait, no, this is actually fine. It was more that this whole thing has to be in from float here. Okay. So, negative 5.87, not within our absolute tolerance of a small number from negative 5.1234. So we did just fuck something up here. Fractional bit here. Interesting. Interesting. I guess it could be on either end. It could be on either end. Does Zig have Frexp? What's Frexp? Okay, so here we take the fractional bits. Can we, I guess we can just test here, as well. I actually don't know how to test this. Yeah, what am I expecting here? I take... I guess we want, like... 1, 2, 3, 4... Hold on. Can we just print out what we get here? Okay. So we get fractional 57448. And if we do... really? If we do... this out of 2 to the power of 16, we get that, right? So that's a bug. Right, because we should be getting 1, 2, 3, 4 here. So what's going on here? 5, 1, 2, 4%, we have 1, 2, 3, 4, like this. 0.1234 times 2 to the power of 16 is this. So why are we seeing something that's not even close to that, right? We should be seeing 8087 here, right? And then if we do 8087 out of 2 to the power of 16, we should see 1, 2, 3, 4-ish. Okay, so it's the parsing that's wrong. So here, the fractional part is this. Oh, I guess it's negative, right? Right, there's probably some bullshit here. Yeah, that's closer. And then our tolerance, I feel like should be fine, right? What's like 1, maybe, hold on. 1 out of, hold on. Like, what is 1 out of 2 to the power of 16? It should be really small, right? 1.5 e negative 5. So this is 1, 2, 3, 4, 5. Oh, I mean, we are cutting it close. So this is a 2. Good. All right. Cool. That is working now. Close enough, probably. I don't know. We're cutting it fast and loose. So now we should be able to serialize a header. This is mostly correct, right? This would probably be like constant from paper, maybe, or from spec, maybe. Okay, so now we have a header, and all we have to do is start shoving in the pieces we care about, right? So in the spec, I guess somewhere we have this is kind of like generate header. then we're trying to generate a no change profile, continue on from here. Oopsies. Okay. Header generated. Maybe. We haven't really proven it yet, but like maybe. Generate no change MVP profile. So what are we doing next? We are trying to inject all the table sections that matter. So if we read this guy. Oh. Oops. He's actually pissed because we need inner here. My bad. U32 has no members. Ford 17. So manufacturer. Oh, I see. So this has to be 0 like this. My bad. Missing field creator. I missed that. So here we does creator allow don't care as well? Yes. Yes, it does. He allows it. Missing field profile ID. What's the rules on the profile ID? Shall hold the profile ID. The profile ID shall be calculated using the MD5 fingerprinting method, whose length is given by the size field in the header with profile flags. But if it is 0, what if I don't give a fuck? What if we just didn't give a fuck? All right. So now we need to add these fields. And not all of them, right? But some of them. So this is like a bunch of like tag info. So we're going to make these sections, and then we are going to find their offsets and write the offsets down in the header, right? Which means that we need to, at the very least, know the size of each of these things up front. Maybe we don't need to know their contents up front, but we do need to know their sizes up front so that we can calculate, right? So I wonder if that's possible, right? The description we can kind of hard code however we want, I think. Let's see. Is there like a minimum size or anything like that we have to care about? Signature of a tag. Offset in the bytes in the beginning of the profile header, which has offset 0 to the beginning of the tag element. All tag data elements shall start on 4-byte boundaries. Okay. And the 2 significant bits of each tag shall be offset to 0. This means that a tag starting with a 32-bit value will be properly aligned without the tag handler needing to know the contents of the tag. Great. Tag data element size should be the number of bytes in the tag element encoded as a U32 number. The value of the tag data element size shall be the number of the actual data bytes and should not include any padding. Got it. Okay. So if we are trying to get in description and copyright, it doesn't look like there's any rules but like 0, right? Yeah, I think that we can say, I don't know yet, we'll see. Sizes is gonna be a stud, enum array maybe, of the, output tags maybe? So we're gonna have some like output tags, right? And we need to have all of the ones that are required, which I believe was in Annex G of this specification, said that we are a 3-component display profile. 3-component display profile. So we need description. We do need copyright. We need the white point, but we do not need the black point. That's optional. Then we need the matrix columns and the tone reproduction curve columns. And we don't need this. Okay, cool. So here we have output tags. And these, I guess, will be U sizes. Maybe U32s? Probably U32s. And how these init values is an enum field struct. So in here, I guess we can kind of go desk is, I guess we start doing this, right? Copyright is 0. White point is 20. RXYZ. GB. all of these are kind of known up front. What about the tone reproduction curves? So here we're gonna have like a curve res maybe, and we'll say we have maybe like 100 points in each. And then we need to say like RTRC is equal to calc curve size with curve res or something, right? And we'll kind of figure this out in a second. And that's kind of it, right? So, yeah, sure. I'm sure there's like a better way, right? Fix me like we can definitely calc size based off type or something, right? That's definitely an option in here. But we'll get there maybe. So okay, what do these curves look like again? They have the header of curve, so we need 4 bytes fixed. Then if I remember correctly, there is then some amount of extra padding here, maybe here. Then maybe the mappings go 2 bytes by 2 bytes or something. Not sure. Let's look at the curve data type. Curve type. Hello, where is it defined? Here we go. So we have this. So we have 12 bytes plus 2 times the number of entries. 2 n? Wait, am I crazy? Oh, yeah, I see. So it's just back to back. I see. So it's like 4. So this is the curve header here. Reserved. This says, hey, you have this many elements. And then here are the entries. So 16-bit number, 16-bit number, 16-bit number, 16-bit number. Got it. So calc curve size is literally just num entries. This is let me think. It's 12 plus 2 times num entries. Easy. Hello? Oh, curve size. Okay, cool. So now we just have to start iterating over these fields and figuring out what we want to do with them. Can you iterate elements of an enum like this? That'd be kind of nice. That would be kind of nice. I guess here we're still trying to calculate the overall profile size, right? So that we can write that in the header. So then the like profile size is going to be the sum of the sizes plus the size of the header, like this, plus like tag sizes, tag segment size of output tags or something, right? Something like this. I haven't quite got there yet. But maybe this stuff goes up here somewhere. I don't know yet. We'll see. Okay. I guess output tags also has to be defined here as well before this. Boom. And so in here, we just need to define tag segment size. So this is based off some type. And I guess this is like the number of elements, like type info of t is expecting an enum, and we're looking for like the number of fields times however many bytes it is per tag header, which I believe it was 12. I believe it was 12 tag table. So this guy has a tag table in here, and each of these tag tables is aha. So we have the count plus the signature. Wait, what? Offset to the beginning of the tag data, size of this thing, and then of the subsequent n-1 tags. Wait, I don't really understand. I don't understand. So this should be a why. So there's a table here. What is the signature for? Byte position 4 to 7 and repeating 12-byte intervals shall specify the signature of a tag listed in clause 10. Oh, I see, sorry. So it's this, then these 12 things repeating. These 12 bytes repeating. So you say, I have 10 elements, and then you go signature, offset, size. Signature, offset, size. Signature, offset, size. It's just weird. It's just weird and funny. So the size of this section is going to be 4 plus 12 times this. I'm pretty sure. Pretty sure. Cool. And then we just need some sizes here. And what is this guy doing? He's like, I want the size of literally everything else, which we've written down here already, assuming that these are all correct. And then I'm gonna actually say that the copyright has a. I bet you, I'm worried about the size being 0 here, so I'm gonna just put size 4. Okay. So what's going on here? What is going on here? I guess we literally just add these up, right? So this guy takes a stud enum array. I guess it's any type to make my life easier. And then for how do you iterate an enum array? What the fuck is this thing? Iterator. Var ret either 0 while it next v you say ret plus equals v value or something, probably something like this. That this thing needs to be returned, so true. What about this guy? Header size does not exist. So this is going to be, we skip the reserve bytes in here, so we're just gonna write it. It's 128. Okay. Iterator doesn't exist in that thing, which is interesting. Wait, why not? Enum array iterator needs to be mutable? Alright. Maybe it's like const iterator? Can you really not iterate over values? Can I just go into like dot values? Maybe that's the play. There we go. Okay, so now this thing compiles. We don't know if it's right yet. But we've calculated a profile size. And so after we write the header, I guess we should have some sort of output file. So this is std fs current work directory open file outs dot icc maybe, or I guess it's actually like profile path like this. And it's not open, it's create. Okay, we need a writer. Writer buff is this, and we say writer is out writer with writer buff. Easy peasy. So now we should be able to be like write header with out writer interface. Boom. Then we should be able to be like write tag table given the output tags. And I think it's not actually the output tags, this is the sizes, right? So write tag table should be it annoys me that the like enum array thing needs to be mutable for the iterator to work. But I guess you can do it this way. You can go like for here, we'll do this. This is a little less pleasant, but whatever. We can say for std meta fields of t field. We are, I guess we start by writing the tag, the number of tags, right? Yes, the tag count is a field is this. We say we have this many things that we're writing out. So like this, int cast here, so that it fits in U32. We're encoding everything as big endian. And then we, for each field, we write the signature. So this is try w write all field name, and I think we need to assert here that the field name len is 4. And then we can write the offset. So var offs here is header size initially. Plus tag segment size t. Right? That's where the data starts. That's where the data starts. And so then we should be able to be like try w write all write int maybe u32 offs big offs plus equals 12 probably, right? Because it's 12 bytes per line. And then we just have to write the size here. So try write table get field I don't really know what's in here. To be honest, something about this is wrong. But we'll get there. Writer buff here is mad because he needs to be immutable. So true. Write tag table, we need to pass in the type, so this is output tag. Okay. And then he's gonna get mad about something, right? So sizes here, expected enums this thing, found this thing, so it's not U size, it's U32. Alright, and then write all. Yeah, this is write int, my bad. Enum field is what this thing is. So how do I get that? Enum field, what's he got? He's got name and value. This is so stupid. This is so stupid. Okay. Inline 4, table values. This is easier, man. 4 table values. Yeah, okay. 4, 0 to fields len, I guess. We say, fields I value. This is gonna be like E is a T is an enum from int on this, which is annoying, but that's fine. We say fields I name len is 4, right fields I name, and then this is table values at I. That's easier. Okay. But index is runtime known, so this is inline for. And he compiles, which is great. So now if we run write without ICC, and then we try to read out ICC, he's getting mad at that he can't read the data, probably, right? Well, he's actually getting mad in the header parsing, which is interesting. Oh, because we don't flush the buffer. We have to flush our buffer. Never forget to flush. Out writer flush. Interface flush. My bad. Write and then read. Yeah, okay, sick. Sick. So we have managed to read our profile back. We have a size associated with him. We have parsed our table. And now we are pissed off because we are trying to read the data that we haven't written yet. Which is great. So now all we have to do is write the data. That's it. All we got to do is write the data. How hard could it be? Okay. So we have to work in RGB space, I think. And we have these tone curves to adjust these things. Writing these tone curves, I think that we start with these linear. This matrix, we need to convert to the their color space. So I think that this isn't used anywhere right now. In anywhere we're using this thing, so I think we can kind of just identity this for now. But what if we didn't want to do that? So if we generate a linear profile for MPV, we need to like have some matrix that goes to the CIE color space from like standard RGB color space. Not sRGB, but just like standard RGB. And I don't really know how that works. There is a matrix here somewhere. This guy. So maybe this is what we use? Maybe. Because what's the sRGB one look like? It is different. Yes, I think this is fine. I think we use this matrix if we're trying to do a linear thing. And then for the tone curves, we just write out linear. White point we write 111, I think, in our color space. Maybe we write the typical their white point so that there's no conversion that needs to be done. That sounds kind of nice. I think. Sure. Okay. So I guess we go for try like inline for the fields of output tags. We have to write something now, right? So we're gonna like say E is output tags enum from int field dot value. We're gonna switch on E, and if it's description, we need to write like a hello world maybe, and we do like write all description. And then we need to pad out the rest, right? So we do like a little splat byte all. We're trying to splat zeros for the sizes at desk minus the description line. That sounds kind of right. Right? Easy. If we see copyright, we're kind of just going to write like none. So we kind of do the same thing here, where it's like none. And we're chilling. White point, I think, I'm very unsure about this. But let's kind of say we have the like D50 white is an XYZ number. Okay. And we kind of yoink this stuff from here. And I think we just set the white point to be the same. I think that simplifies things. So this is D50 white here, like this, and we should be able to be like, okay, what does it look like? The D50 white point, I think we need to write the type out first, right? If we look at the white point that we get when we read these, it is XYZ space, 4 bytes of null, then the 16-bit versions are the 16-bit versions of these things. Or just the output as they wrote it, I guess. Right? I think so. So writer interface, write all XYZ. And then we splat byte all 0 4 times. Then we write our thing. So we try writer, I guess it's like we have the writer for this already. So it's D50 white X write, or it's even D50 write, like this. Right, and this will just write out the raw bytes of these things? Yeah. Perfect. Perfect. Easy peasy. Then we have RXYZ, G and BXYZ. And what are we going to do here? This is one of the numbers in the matrix. Can this just be identity? Maybe. I'm not sure. Right spot header. I know. I would like to be clear that when we write shit code like this, we are very aware that it's shit code and there's duplication, but I like to bang out the shitty version first and then fix it later. I feel it's nicer to me. Like for example, like this tag. Obviously, this shouldn't be written this way. Obviously, we shouldn't be slamming these like splat byte alls everywhere, right? But it will just be easier for me later to like see where the commonalities are now when I'm writing it the stupid way, and then later I can come back. You know what I mean? You know what I mean? But I agree, it's shit. So these are the same. These are the same. I just prefer working that way. It's fine. It's fine. Okay, so we are writing. I guess it's like S15. No, it's not S1516. It is a XYZ number. Then we write this thing after like this, right? Which he doesn't seem to like. Maybe like this, he likes it. So X is going to be from F32 of 1. And then I think it's like YZ here is zeros. And then this guy is going to be very similar, but like this, and B is just going to be the last one, I think. So that should make an identity matrix, I think. When was the last time you saw code you weren't discussing? But I think that like by the time I commit stuff, I'm usually pretty happy with it. I think. Wait, are we forgetting to write? Oh, we already wrote off the sizes and stuff, right? So I think it's fine. So now we just do the tone reproduction curves. So we have our TRC, and we are writing out. What does it look like? It's like the word curve. Curve, 4 bytes, number of entries, entry, right? So it's curve, pad, num entries, entry, right? And right for now, we are literally writing the same tone curve for all 3. So I don't have to worry about this. So we write the word curve, we splat byte all 0 4 times, we slap the number of entries in here, so writer interface write int as a U32 of the num entries curve res, I think, and we write this in big endian mode. Got GXYZ twice. Oh yeah, thank you. Thank you. And then we just go for 0 to curve res. I guess we do a little U16 write of I times std math max int of a U16 out of curve res. That sounds right. I think that lines up. Big. And I think we're almost there. Expect U16 found U size. Yeah, so true. That's so true right now. And if we read it, it looks like he gets mad. That's interesting. Okay, so who's he pissed at? He is pissed at data for description. He never finds it. Oh, is this because I did all this after the flush? Sure is, huh? So flush has to go at the end. Okay. Good news to some extent. So looks like we got the description right. Copyright is not right. All of this stuff is still nulled out for some fucking reason, right? Which isn't good. So it's either because the offsets are wrong or because we didn't write this stuff. Both are very possible, right? So I guess what we do here, Are you interested in the hardware computers? You're more of a software, Andy? Probably more of a software guy. Hardware is pretty interesting, but I'm not that, like, you know, not that into it, I guess. Less experience. Okay, so we do see this none here, right? At 130. And our curve data, when we read this thing, copyright is at 252, but this is in decimal. So, what is like 130 hex? 130 hex is 304. So the header offsets are wrong, or our sizes are wrong. So what I want to do is I want to say like expected end is going to be W writer interface, like, is there some sort of like written? There's something about this where you can like ask how far into the file we've written. I just can't remember what it is. Written? I'm pretty sure there's some way for us to like figure out how much we've written. We have buffered. I swear I've seen this. In what point you write GXYZ? I write XYZ here, but that's normal. That's expected. I swear that there's some way. Zig standard library. I swear I've fucking seen this. Where you can say, tell me how much data has been written to this file. I know it's in here. True seek position of the file. Add the buffer size. Oh, you just have to do it manually. Writer pause plus this. And then we can check. This is like plus sizes get E, right? And then here we can check that we actually got there. Actual end is this. And std debug assert that actual end is equal to expected end. Did we write this out how we expected to? Probably not, right? Oopsies, no seek. What is it then? End. Oh, interesting. Interesting. I don't know what to do with that information. So this is not crashing. So we are writing out sizes that match what our calculated sizes are, which means that it must be that the tag table is wrong in some way. So offs here comes from the header size plus the tag segment size. So what's also very surprising here is that the first field is correct. Right? So we see description 64, and then copyright is not 64 higher. Right, so that's the bug here, is that the offset is not getting incremented right. Yeah, because this offset needs to be incremented by sizes. I'm an idiot. I'm an idiot. Much better, dude. So this parsed correctly for us now, right? We see description here, copyright none, white point here, RXYZ 1, 1, 1 for RGB, and then we see 3 curves. So I think that this is kind of right. The next thing to do is try to open this with MPV and see if it loads there. I believe. A copyright for an ICC gamma curve? Yeah, it's actually required. Believe it or not. Okay, MPV, ICC profile, out ICC, and let's see if this guy runs. Okay, good news, he runs. Bad news, it does not behave at all the way I expect, right? So this is like really pitch black, which is interesting. I would also like to see what happens if I apply this to my monitor. You guys won't be able to see this, but it's kind of like a fun little thing for me, just for information. So apologies for the unhelpful stream, but I'm curious. Okay, so the good news is it parses and loads. It is not useful. It's not doing anything sane, but it is generating. So we'll call this generate any profile, and we'll call this complete. And now we have to try to generate one that does what we want. So this is generate no change MPV. And this is not done yet. Okay. Maybe it would be interesting. Can we do something where, can we look at this thing in LibreOffice? I believe as part of our parsing, we export a CSV of the data, phone, photo, and post Discord. Yeah, maybe later. Probably not though. It's fine. It's fine. It's not important enough. It looked maybe what it would look like. Oopsies. RTSC.csv. Okay. So what do we see here if we insert a chart? Okay, so the good news here is we are generating a curve that is linear. It's just fucked. So the next thing to try is we generated just like a raw identity matrix for our RGB thing. Maybe that was wrong. I think that we originally said we were going to try this and I just fucking forgot. So can we do that instead? Can we do that instead? So this was going to be like this. So the R is 0.049. We can do this. 0.17697. 0. G 0.310, 0.81240, 0.0100. Blue 0.2, 0.01, 0.99. Let's just see what happens if we do that. Let's see what happens if we do that. MPV. Oh, okay. I mean, it's interesting. Very interesting. So, it turns out this matrix is doing something. Shocker, I know. But yeah, you can tell. So if I just like nuke all green from this or something. Oh, that's actually close. What the fuck? What the fuck? Oh, surely it just uh, surely that's because the profile's corrupt. Yeah. Yeah. That makes more sense, right? We entered something like so garbage that it couldn't figure it out, which makes sense because we just put something invalid. So okay, what we do know is, sorry, brain, is that if we do an sRGB curve, um, we know that if we apply a scale matrix to the sRGB curve and then output the sRGB curve, we get something that we could kind of see in MPV. We now also know that this matrix is relevant in some way that we don't fully understand. We also understand that, I mean, it's very likely that this is the wrong matrix, by the way. Very, very likely. So, because this is from CIE RGB space, is there like, this might be worth asking the fucking idiot, to be honest. This might be worth asking the idiot. What gamma are you trying to generate? I'm trying to generate something that like has 0 change in MPV with like a linear mapping. If I can you help me generate a matrix that goes from linear RGB values to CIE space? I think this is different than the sRGB to CIE and not just like, and very much not identity either. I just kind of want like to understand something. We can try, if he gives us something, maybe it will be useful. Okay, this is interesting. So we can see that he's talking about like going from D65. These matrices map from the specified RGB space, primary is D65 white, to CIE with the same waypoint. So okay, let's see what he says, because we don't understand something. It converts a linear RGB triplet in a given RGB color space to CIE with tristimulus Y is approximately relative luminance. Yep, because the matrix depends on RGB primaries, which I don't understand, and the RGB white point. I'll make a reasonable assumption that you mean a common linear RGB space. Specify which if you need a different one. Right. Below are matrices for the 3 common linear RGB spaces linearized from their encoded forms. sRGB D65, Adobe D65, and Display D65. Uses when the RGB are already linear, gamma removed. If your RGB are a different RGB working space, tell me the primaries. Okay, so does this look like anything that we've seen before? I mean, he's just copy-pasting this, right? This is just this matrix. But it sounds like an important step. Yeah, it could be. It could be, yeah. I mean, I understand, but I thought that we're not really using any gamma at all. But it sounds like he's kind of there's an argument to be made here that like this color transform is applied after sRGB removal. And I think we saw that actually somewhere in the like AMD docs for the cathode braid tube control pipeline, that like they remove the like extra mapping, extra lookup table, then they remove sRGB, then they apply the matrix, then they apply sRGB, then they apply extra stuff again. So it could be that this matrix is already working in linearized space, like the idiot is saying. In which case, maybe we try this matrix and see what happens. We can always try and guess and check. That's what I've always said, and that's what I've been saying. I don't know what the fuck I'm talking about. And we all can tell. You all know. But we try this, and if it works, we can kind of, I like reverse engineering the answer from our results. You just say anything, try anything, and then if it works, you go, I must have been right. This also looks like shit. It's like flattening out the fuck out of all the darks, which is very interesting. Yeah, very interesting. Very, very interesting. Also, I think that this stuff is all tinted yellow. I think everything is tinted yellow. Asking it for without the gamma removed? Maybe, yeah, that's a good point. Oopsies. Can you do it without the gamma removed? But I thought that I was taking the gamma out already. This is just the same thing, right? He's just writing the same fucking matrix down again. Yeah. I don't trust him. I don't trust him. I'd also... Okay. So, can we try generating an sRGB curve and then figuring it out from there? So instead of writing in these things linear, can we write the floating point version of this value is I floating point. We do f point divided equals by curve res. When we do 64 here, then we do a little stud math how floating point to 2.2, which isn't quite right, but it's like kind of close enough. And then we do we write this as an integer as int from float of val times stud math max int u16 or something. Float from int or something. Expected 3 arguments, found 2. So true. So now we're getting closer to real sRGB, which this is now looking kind of close to, right? So this is with the profile applied. And if we do not use our profile... Okay, we have this, and we have this. These are very similar. Not quite, right? We can see that ours is kind of like a little darker here. But this is very close. Now, what's interesting here is Nu is also a bit yellowish. Yeah, a little. Yeah. You can tell. I agree. This is a bit yellow. And I bet you that this is related to the fact that sRGB is in... First of all, we're not using the correct sRGB curve, which we should fix. 2, our color matrix might be wrong here, right? Because we said before that we have to... the other profiles that we have are also applying the white point conversion from D65 to D50. So let's kind of like step that in a couple steps here. So can we look at like the real sRGB curve? Is it different for RG and B? No, right? They're all the same. So it's just this, right? This is a perfect place to add a decal literal to that type so you can quickly select different matrix values. Yeah, not a bad idea. So this is over 12.92 for R if... Okay. If F pitch is less than or equal to 0.04045. It's one thing, which is F point over 12.92. Else, it's some power thing. But not whatever you would expect. It's R plus plus 0.055 over 1.055 to the power of 2.4. And then we could try that. See how that looks. Oops, this is without the profile. This is with it. Interesting. This looks a lot like, actually, this is starting to look very close to the way that it looked with the default profile. Like, if we do ICC profile of this sRGB profile that we have. Hold on. The, like, way that it's dark feels right. Why the fuck didn't that load? What the fuck? Am I stupid? This works? sRGB 1.0. There we go. Right, like, we still have our yellow tint on ours. This is yellow, right? You can see the yellow tint here. But, like, the darkness look is actually very similar now. So we're at least generating a profile that's similar to what we've seen in the past, whether or not it's, like, what we expect to see, as in no change to the original input video. So I think that that's going to be this, like, matrix thing. Yeah, so why, hold on. Why does the linear one look so shit then? There's something interesting here where, like, I don't really know what I'm looking for here, to be honest. Like, it's almost working backwards from how I would expect. I think. I'm, like, increasing. So, like, from linear to sRGB. From linear to sRGB. Our display is getting darker. But the video is getting brighter when we add this gamma, which is confusing. Can we do something like this? Let's just apply a gamma value here, just like straight up. So we start with gamma 2.2. Are you still using idiot values and not wiki values? I'm pretty sure I'm going to wiki values. Pretty sure. So can we just do like std math pow floating point gamma here. Okay. And our matrix is doing something, but like whatever, fuck it. And I just want to see if I start like cranking this up. So this is kind of like gamma 2.2. And if I crank, I would expect that if I go up, it gets darker. That's what I would expect, and I probably am missing something if that's not the case. So, hold on. So this is higher gamma, and this is lower gamma. So this is brighter on the right, actually. And is that true still if I display on my monitor, not just on the video. I want to confirm that as well. Move out ICCs. This is G24 and or 26, I guess. And can we go 2.2 as well? Move G I guess Zig, right? Move out ICC G22. And if you guys won't be able to see this, but is the darker version, which one is darker is the question that I want to ask myself right now, which should be easy to tell myself. So 2.6 versus, you guys can't see, but everything got brighter on 2.6 on my screen versus 2.2. It is the same. Interesting. So what don't I understand? Can we read G22 ICC? Is the curve that I'm generating like reasonable? So here we have LibreOffice. Am I generating what I think I'm generating? Let's just take a little peek skis. So, oops, this is the wrong file. This is the one I wanted. So we are looking at, yes. So if okay, if this is the 2.6 curve, hold on. Oh, that was the 2.2 curve. So move RT/RC to 2.22. And we have the 2.6 curve, which we can do generate by doing this. And then we move RT/RC CSV to G26 CSV, I think. LibreOffice G22 CSV. What? Oh, it's 22. Move 22 CSV G22 CSV. Okay. So with 2.2 gamma, I would expect that as we increase the power, it kind of like slopes in further. That's what I would expect. So we have 2.2 and 2.6. And I want to copy this here and chart both of these. Right, so we have B is 2.6, blue is 2.2. In my mind, this means that the display is squashing the darks more, right? So farther to the left on the darks, we are keeping the number lower, right? So more numbers should be darker. But by increasing it, wait, which one was brighter again? On both the ones, the curve that I would think squashes the darks more ends up looking brighter in the darks. But I wonder if that's related to like the color matrix as well, because we just kind of have this like hard-coded thing in there. Nothing here is behaving the way I expect it to. Try again with 0.045. I agree. That sounds interesting. Okay. Zig run on write mode out. So can we then MPV this thing? Let's just like, I mean, this is like turbo fucked. Turbo fucked. Can we try like maybe 1.5? 1.45? Also, just really, really, really dark? Or 3, so 0.45 really, really, or 1.45 really, really dark. 3 should end up being really, really bright, according to how this thing has been behaving. Yeah, look at that. I'm on Kevin's side. Something's really wrong with your base values. Did you use columns or you meant to use rows in the matrix? Did I? I don't think so. But we can double check. It's worth double checking. I mean, okay, so we have, annex G was where this thing is defined. It is worth checking. Red matrix column tag. Right, so this should be the column used in the matrix used in transforms so this is the value that red would be multiplied by. I assume. Maybe I'm misunderstanding here. But this sounds to me a lot like value of red, right? Which means that when we look at this matrix, wherever the fuck it is, that red here gets multiplied by this and this and this, right? Which should match what we have here, right? So we have the column here copied into the red value, wherever the fuck that is. Where'd it go? I lost it. Here. So 4, 2, 0, 1, 3, 7, 1. So I don't think that I'm using a column when I meant to use a row, right? Blue, this is like the blue XYZ. So blue X, blue Y, blue Z. Feels correct to me. It's more about the idea that, like, the gamma is behaving in the opposite way that I would expect. Do I have it all backwards? Do I have it all backwards? That would make some sense, maybe? Hold on, let me think. So I thought from the start, from the start, that this red line is what the monitor was outputting. But maybe this red line is what the sRGB encoding of the data is. In which case, it would be flipped. No, that's what you're telling the monitor to output. Okay, I mean, if you're agreeing with me, I also agree. Plot of the sRGB intensities. That lines up. Because, again, we want more resolution in darks, which means that the output of the sRGB needs more value in the darks. All of that lines up with everything I've read. So, yeah, I agree. But then in that case... Oh, somebody's saying, on the wiki notation, R gets multiplied by the first row. Did I forget my algebra? Am I stupid? Am I stupid? Where are you guys seeing what you were saying? I don't think you're matrixing right. What do you mean? You do... Look, matrix multiplication. Matrix multiplication. You do column by row. Column by row goes to output, right? So we here are doing column by row. So RGB gets multiplied by the first row and the second row. And you can try the transpose version, prove them wrong. Oh, but also we have proof, by the way, from yesterday that we understand this matrix. Because we generated this matrix, so in these matrices, we have these sample files. We have these sample files at like sRGB 1.0. And in here, we see like matrix values here for RG and B. And we constructed these. So first, these are not exactly these numbers, but we constructed these by reapplying white point. Proof that also generated two images that were unexpected. True. But these numbers were consistent across multiple profiles. And they worked reasonably in KWin. And didn't show up the way we predicted. Yeah, all that is true. I agree. I'm just trying to think what I want to do next. Because it's 420, blaze it, peace up, whatever. But so maybe this is like a good place to like think about it overnight, right? We have a profile that we've generated. It's not behaving the way we're expecting, but it is generating, and like we have like consistency here. Our big question right now is what is supposed to go in this color transform matrix relative to the curve data. If your predictions are incorrect, you can't make more predictions, assume they're right, you gotta try stuff to prove yourself wrong. I agree, but what we try, I think, is important. And I also am not 100% on the side that MPV is doing something that's correct. I'm not on that side yet. So, I'm gonna think about this overnight, I think. I think we're close. Because we can generate whatever data we want now. It's just the data that we're generating is not interacting with the profiles in the way we expect. So I think that I'm going to do some more reading about the profiles overnight, or maybe in happy hour tomorrow, and then we can try to implement a fix in the main segment tomorrow. I think that makes sense. Cool. All right. We can call this a success. We haven't been able to generate a no change thing. We do have to generate a thing that changes stuff. Or just have darker darks. Yeah, just fuck yourself. Yeah, we can just don't make what we wanted. Yeah. Anyways, thanks for watching, guys. If you like what you saw, we stream most days. We aim for 12:30 to 4 Pacific time. It is 4:20 now. So if you're watching live, anywhere between 4 hours and 30 minutes ago is about when you should expect to see us live. We're working on this color profiling stuff for now, but we will be back on the Wayland Compositor when this is done. So keep an eye out. YouTube, Twitch, Patreon, you can support any of those places. You know, I make like 1/10 of what I made as a software developer right now. So any amount of money that I make allows this project, not this project, the project of streaming to continue for longer. So please consider supporting if you want. In return, you get access to the parts of the streams that I don't post in VOD form. Obviously, you can catch them live for free, but if you want VODs, support somewhere and you get those. Otherwise, I think that's it. Thanks for watching. Hope you're having a good day. YouTube, peace out, and Twitch finds someone to raid.